Hello, can you hear me?
Hello?
Hi, can you hear me?
Yes.
All right. Let me know when. Hello, can you hear me? You want me to?
Let's go.
Hi, this is Curity. This
Hello?
is Curity. Hi, can you hear me?
Yes.
All right. Let me know when.
Let's go.
Hi, this is Curity. This
Hello?
is Curity. Hi, can you see my screen?
Yes, I see.
Yeah, I can.
Okay. Okay. Yeah, let me know when you guys are ready to start. We can wait 5 or 10 minutes before people come in. So can you see me?
I can.
Okay.
Sorry, that was mine.
Oh, yes. Okay.
Yeah, sorry. Is yours an hour long?
I think I can do 45 or 40 and then take some questions if there are any, and then I can start.
Trying to fix that.
But you can hear me all right?
Yeah, I can.
Okay.
Because I don't think mine is going to be more than like 30 minutes.
Yeah, that should be okay.
Let's start.
Or did they mess up the time? Because I don't see anybody else. Let me try to share my screen. Okay.
Let's start.
Now you want me to start? Or should we wait for a couple of people?
It is in translation to YouTube, and your presentation people see in YouTube.
Oh, okay. All right. All right. Good morning or good evening, everyone. Today's talk is about OpenVX 1.3 and Open Standard for Computer Vision Software Acceleration. And I'm Kiriti Gowda. I'm the OpenVX chair of the Kronos group, and I'm also the senior staff engineer at AMD. And today's agenda, we'll go through what OpenVX is. We'll just quickly define what an open royalty-free standard for computer vision is. And then we'll take in a deep dive into OpenVX 1.3, which is the current standard version. And then we'll see what our conformant implementations are. And then we'll go to sample applications, and we'll see some of the case studies from different vendors like AMD, Cadence, and others. And then we'll talk about some of the open source tools available, and then we'll see what updates we have for OpenVX for Raspberry Pi, and talk about some of the new features and what people could do it on a Raspberry Pi. And then looking into future, we'll see what to do with camera extension and talk about our future work there. And then at the end of it, we'll wrap it up by summarizing what we talked about, and then we'll take up any open questions if people have it. All right, to start with OpenVX, those of you who are not familiar with it, is an open royalty-free API standard for cluster acceleration for computer vision applications. So you can think of OpenVX as an API which supports computer acceleration on multiple different hardware platforms. And this is due to because the vendors or the hardware vendors themselves implement OpenVX to be used on their platform. One of the advantages of OpenVX is its high-level graph-based abstraction for portable, efficient vision processing. So OpenVX was primarily designed to be shipped by the vendors so that when people want to use some of the computer vision nodes, they don't have to handwrite optimized code for their platform, but actually use available OpenVX from the hardware vendor through the driver. And the implementation has the performance portability because the API remains the same, and across all platforms you use the OpenVX, you should get comparable performance without having to change any of the application source code. And in your application, you can contain both the computer vision or neural net nodes and the graph optimizer within the OpenVX actually optimizes globally for your graph. And then talking about runtime graph execution, it needs very little host interaction. So you could do more on the available processes. So let's say you have a graph which you want to run on the GPU, and then you have another graph which you want to run on the CPU. It is possible with the OpenVX. All right, this is how a typical OpenVX node looks like. So if you see, we have on the top level a graph where we have some vision nodes, and then we have CNN. So CNN is primarily supported in OpenVX through NNEF. So NNEF, talking about it, it's a neural net exchange format. So it is an open source format from Kronos, so that people could train in whichever framework they want. And then once they're done and they want to deploy this network, they can convert it to one of these open source networks and then run it across. And this is how a typical OpenVX application would look like. So if you're doing something like machine learning, you'd have an input image, and you run it through a source vision node where you could do some kind of filtering, or you could do some kind of image augmentation to it with that node, and then you can pass it through the CNN node. And then once you're done with your inference, you could do some post-processing like drawing boxes or something with another vision node. And then you can view it or send it upstream, or you can even stream it on YouTube. All right, as I said, OpenVX primary goal was portability and making the performance portability in as a primary goal. So since the inception of OpenVX, the API had grown and it had extensive set of functions. And with 1.3, there was a view of the API to actually make sure that there's no fragmentation with the OpenVX API. So what we did is we created something called feature sets. So basically, feature sets you can imagine as a group of functions which have similar functionality grouped together. So what we did is, instead of having this whole bunch of functions in one pool of and call it OpenVX 1.3, we split them into multiple feature sets. And then when a vendor wants to implement, he can implement either like a vision feature set or a neural net feature set, whatever feature set he's interested in. And this was one of the key features with OpenVX 1.3. So basically, this let anybody who wanted to implement OpenVX or use OpenVX be clear that, okay, their sets of functions are available and it's supported by a given hardware vendor. So the feature set clearly identified what feature set was supported on the hardware and what kind of applications you could run. So in the conformance feature set today, in 1.3, we have the vision feature set, we have the neural net feature set, and the NNEF feature set. The vision feature set hasn't changed much since 1.1. So the core vision functions are still the same. So we have all the functions which we put together in 1.1. And then we have a neural net feature set, which is almost equal to 1.2 features, and it has more neural net extensions and tensor objects. And then we have NNEF import conformant feature set, where you can actually train your network. And when you want to deploy that network, you want to convert that into an NNEF node, and then you launch it with the OpenVX graph, and so basically it works as an import node. And then you have optional feature sets, which are the U1. Basically, you could do the whole graph processing just using binary images. So that was one of the optional feature set which people can use. And there's enhanced feature set, which has more advanced vision functions if people need it. And there's base feature sets like the graph infrastructure I was talking about, where you can do the global graph optimizations. And then we have also the deployment feature set for safety critical usage. And talking about conformant OpenVX implementation, so we talked about vendors and others. So basically what a conformant feature set is, a conformant implementation of OpenVX is basically one of the vendors uses the API created by the OpenVX working group, and they implement their version of OpenVX, and they actually run this implementation through an exhaustive conformance test suite. So once they pass the conformance test suite, they submit the results to the Chronos, and the working group verifies that their implementation was actually correct. And then once we verify that, we award them the conformance award. So basically this can be used by the vendor to say that, hey, my implementation is conformant. So basically, which means if a developer uses one of these conformant implementation, he can be sure that if he uses any of the conformant implementation, his results across different platforms would remain the same. And because he's using one of the implementation from one of these hardware vendors, he'll get the best performance from their hardware because they know their hardware best, and they would have written the application, the underneath OpenVX to the best of their knowledge. And as you can see, we have most of all the popular silicon vendors have their own implementation of OpenVX. So if as a developer, you choose to use OpenVX within your application, you can easily make that transition from one platform to another and also get the best performance while you're doing it. And let's go into some of the sample applications. Or basically, this is a case study talking about what these conformant implementations by other companies are being used at. So this is one of the examples from Cadence. And you can see here, this is a background subtraction for video security. So you can see on the center image on the top, there's a dog running through chasing a ball. So basically what it's doing, it's taking out what is active in that frame versus what is inactive. So you can see in the picture below in the center, you can pretty much see just the dog and the moving ball, and everything which is static is taken out. There's a very simple background subtraction for video security to do some kind of motion detect and stuff like that. So you can see the graph on the left. It basically does some resize, accumulate, and it goes through threshold, dilate, erode, and then you get your results. So on the right, the interesting thing is you can see the memory latency here. So as the more higher the memory access penalty, the greater the graph benefits. So basically, using this graph structure, the grapher optimizer can optimize your application to get the best performance and memory optimizations that as a developer, you don't need to worry about, which is handled by the implementation itself. So here's another example of reliable motion detection. That this is from the access communication. And here you can see what they have is a tool which they created. It's called a graph drawing tool. So basically, as a developer, you would just take your application and then you draw as a regular graph. And then once you draw the graph, their tool will go through your graph and generate an OpenVX graph, which is shown on the extreme right, where it takes that diagram, which is basically a graph, and then converts it into an OpenVX graph. And this is another example from Texas Instruments, and this is talking about their front camera ADAS use case. So basically here they have a whole bunch of computer vision and neural net nodes, and you can see where they have marked where these individual nodes are running. So they have some nodes running on DSPs, some other kind of basic hardwares, and whatever they have special IP hardware. So within one graph, they can schedule their graph nodes on different hardware and get the best performance from that hardware. And as a developer, you don't need to worry about moving these nodes from those hardware, underlying platform hardware, so that you can get the best performance from your application without having to know which node to run on what hardware. So this is handled by the application itself. So you can see an image coming through. So it's doing traffic light detection. It's doing some kind of object classification. And basically this is for avoiding front collision. And it warns the driver that there's some object in front of him. So here's another example, and this one is from AMD. This is just showing a neural net use case where you use any of the framework to create your model. And once you're done with training your model and you have a deployable network that you're confident about, you're going to convert that into one of the open exchange formats, either Onyx or NNEF. And then once you have it in that format, you can pass it through MI Vision X, which does the model compiler and optimization. And then it converts it into an OpenVX graph. And then once it's done converting into a graph, and then you can run the whole neural net application with a few computer vision nodes as an OpenVX graph. So here's more of how it's doing it. So on this example here, we have a YOLO V2 is running through the MI Vision X model compiler. And once MI Vision X generates an OpenVX graph, so and you can create an application with the tools available from MI Vision X. So talking about all the open source tools which are available currently online. So I talked about the Access Communications OpenVX graph parser. So basically this tool, like I said, you could try it out. It's available open source on GitHub. So you would download this tool, you'd link this tool to any of the conformant implementation. And then once you're done with it, all you have to do is draw your application in terms of graph. the parser goes through your graph and then it converts it into an OpenVX. So you can see it takes your simple graph on the extreme left hand, and it runs through its own graph parsing and creates the OpenVX code. And this tool could be used by developer using any vendor's implementation, which gives you performance depending on what use case you're looking at on what hardware. Here's another tool that we have, which is called the RunVX. So basically, RunVX is a command line tool to execute OpenVX graphs. So basically, instead of writing your whole OpenVX application in C or C++, you'd basically write this in a GDF, which is a graph description format, and which pretty much looks like the one on the left-hand side. Basically, you write the graph in a very descriptive way, human readable, and the RunVX goes through this and generates the OpenVX code for this. And this is also available open source with MI Vision X. So if you're using AMD's tool for OpenVX, you could use RunVX to quickly prototype and try out any application you want to develop. So here's another open source tool that the working group is currently working on. It's the Python binding, and we call it the PyVX. So basically what it's doing, it's taking all the OpenVX API and it's making it available as Python functions. And this will be available open source on GitHub. We'll post it on the OpenVX website. So those of you who are not familiar with Khronos and OpenVX, I would recommend you going to their website and looking through the OpenVX literature. And we'll have this up sometime by the end of this year. And this will give developers an opportunity to use OpenVX within a Python framework and get optimized vision functions, which are optimized on that hardware without having to worry about the performance inside a Python graph. All right, we talked about the OpenVX for Raspberry Pi. As Raspberry Pi is one of the vendors for OpenVX, and they actually provide their open source implementation of OpenVX on GitHub. And this is hosted by the Khronos sample implementation. So basically, the sample implementation has a version of OpenVX which runs on Raspberry Pi, and it's optimized for Neon architecture. And here's what the overall structure of that implementation is. So basically, it has a vision, enhanced vision, and the neural net feature set. And if you choose to use it on a Raspberry Pi, so you could use any of these conformant feature sets for your application. And then the supported hardware is the Model 3 and Model 4. And basically, here's a sample example that we actually also provide is doing an MNIST NNEF model. It imports it with other computer vision nodes and it creates an application. So basically, if you want to try out OpenVX on a Raspberry Pi, and it's available on GitHub. So in terms of future work for camera extension, we are actually working on creating a reliable camera extension with OpenVX. So as you have already recognized, if you're already using OpenVX, is OpenVX relies on libraries not within OpenVX API, but on the operating systems it's running on or other platform to get access to the camera. And this always has some limitation because these libraries could be too large for embedded systems, or libraries have different functionality gaps. So if you're using one camera API on, let's say, a Linux platform, and if you want your application running on Windows, those camera API might not be supported on Windows. So basically, then you have to report your entire application for Windows. So to solve this gap with the camera API, OpenVX is trying to come up with an API, or at least work with the camera group within the Chronos structure to come up with an API extension which will allow the developers to run their graph across Linux, Windows, or Android, iOS. So basically, the limitation of the API being it will be very modular and very simple, and it might have just a few functions like the initialize, reinitialize, capture, release, get attribute. So just enough to get people started and start using the camera. And for advanced users, you could always unlock the advanced features within the API and not through the OpenVX extension. So once the image is captured, the OpenVX will wrap the image into an OpenVX image, and then it runs through the whole graph as it would in any other graph. So, and then this would allow basically the developer to move his application easily across different operating system and across different hardware vendors. So like I mentioned, with this regard, the camera extension is worked on with the Chronos group and then the embedded European Machine Vision Association. So they're pretty active right now. And those of you who are interested could, it's open for public at no cost, or you could join the discussion. There is a link here. We'll probably post this presentation at the end. So if you're interested, you could get involved. All right. To summarize, in terms of what we've learned so far, OpenVX is unique in being the only vision API shipped as optimized driver, and the OpenVX delivers performance comparable to handwritten, hand-optimized portable code. Why I say this is because each of these implementation is written by the hardware vendor. As a developer, all you would do is use their implementation to get the best performance, and then you would not have to worry about optimizing the underneath vision functions. So it's pretty much like you're getting the hand optimized non-portable code for your particular platform where OpenVX is supported. And like I said, the acceleration is available on a wide range of hardware architectures, right from DSPs, x86, graphic processors, and many other. And if you want to get a full list of it, it's available on the OpenVX conformant hardware list. And then, as you already have seen, OpenVX has great benefit from using the graph level optimizations, and this graph could be launched on almost any hardware or processor. And that being said, OpenVX is portable and it's efficient vision processing. And I'd like to thank Mike, the Director of Software Engineering at AMD, Neil, President, Chronos Group, Timur, for arranging this talk, AMD's MI Vision X team, and then the OpenVX Working Group and the GraphiCon 2021 organizers. With that, I have a few slides on resources and material that people can go through. So here's some of the material on sample implementation, and then we have sample application. And those of you interested in doing like a tutorial, we have a self-guided OpenVX tutorial available. So basically over here, the sample implementation, if you're looking to run your application on like x86 or iOS or something available to you, it's great to use the sample implementation, but it doesn't give you the hardware acceleration that I'm talking about. So if you need an efficient OpenVX for your particular hardware, you're going to go get the implementation by the hardware vendor and not use the sample implementation for your probably like a deployment application. So you could use the sample implementation for trying out prototyping, but like I said, the sample implementation doesn't have the optimizations that I talked about. So if you want to run on like an x86 processor, you could pretty much take AMD's MI Vision X and use the OpenVX from there, or Intel's, depending on which hardware you have. And then if you're trying to do on the same, like a graphics card, you would either use AMD's or NVIDIA's VisionWorks. And with that, the whole API structure is available on the Kronos API registry. And the OpenVX Raspberry Pi that I talked about is also available. And all the examples which I talked about from MI Vision X can be accessed on their GitHub page. All right. With that, we have time for questions. Does anybody have any questions? All right. If you do have any questions, and if you're viewing this presentation on YouTube, feel free to leave your questions on OpenVX GitHub page, or even on our OpenVX website. There's a link for developers to leave any questions or any issues that they're facing with OpenVX, and the working group will try to answer all your questions. And I think the Graphicon organizers will host the presentation somewhere that you could get a hold of. All right. Thanks, everyone, and hope you all have a great day.
Okay, thank you very much.
All right. Did you want Lakshmi to start her presentation right away?
I think Raji is also here, so.
Yeah, I was going to ask, should I wait till 8 a.m. or start right now?
Because I think it's live on YouTube right now. So people are watching on YouTube and not on Zoom.
Oh, that's why I don't see other participants here. Okay.
Yeah. Yeah. So you could start your thing if they want you to, because it's going to be available on YouTube anyways.
But I need a confirmation.
Okay.
Yeah.
There is the organizer here.
Hello. Hi.
Yes, I do.
Hi. Yeah. My name is Raji. I am also going to present at. It was supposed to be at 8. So since Kiriti finished it earlier, so you want to wait till 8 or start early?
Let's start your talk.
I can start my talk now.
Yes.
Okay. All right. So Lakshmi and Kiriti, you are also here, right?
Yeah, we're here.
Okay. So let me share my screen. One second.
You can start.
Yeah, I'm just bringing up the PowerPoint. Mhm.
You can sharing.
Yeah, I'm just doing that. Do you see my screen?
Yes.
Okay. I need to get the speaker view. I don't see that. Do you see my my camera is sure.
No camera.
No, we don't see you, Raji.
Okay, so I need to turn on the camera from the Zoom, I think that's why it was not.
Yeah, we see you now.
Okay, 1 second. All right. So, am I audible? Can you hear me?
Yes.
Okay. Do I need to increase the sound or something?
No, it's good.
It's good. So I'm going to start now then. So my talk today is an analysis of data augmentation techniques in machine learning frameworks. So hello, everyone. Many of you might have heard about Ivan Pavlov, the physiologist who was researching salivation in dogs in response to being fed. He predicted that the dogs would salivate whenever the food was inserted in their cheeks. But what happened was they started salivating whenever they heard the footsteps of someone who was bringing them the food. So what happened was the dogs got trained too much to the extent that they started memorizing everything associated with it to produce an unwanted outcome. This phenomenon can not only happen with Pavlov's dogs, but also while training a neural network model. So today's talk is about how to prevent overfitting in machine learning by doing data augmentations. With that, let's look at the agenda for today's talk. So first, we will explore why data augmentations are needed in machine learning. Then we'll dig into some different kinds of augmentations and their use cases in computer vision. We'll also learn about the importance of random parameter adjustments and some common pitfalls. In the end, I will go through a machine learning training pipeline with augmentations and conclude with some challenges. So do you remember the internet controversy behind the color of this viral dress in 2015? So many of us were like confused about the color. Some people predicted it to be blue and some others predicted it to be gold. However, a well-trained image classification neural network model today can predict the color of the dress with more than 90% accuracy, with enough variation of blue and gold dresses in the data set. Neural nets don't have misperceptions of data like human beings, but they can definitely learn from poor data. That boils down to the burning question for today's talk. How do I get more data if I don't have more data? So as you may know, the ImageNet has over 1.2 million training images and 50,000 validation images and 150,000 test images. And a typical image classification convolution network has millions of parameters and thousands of neurons to train. This can all lead to the problem of overfitting. So overfitting occurs when the model fits too much to the training data to the extent that it performs poorly on unseen data, as it is shown in this diagram here. So here, as you can see that after a certain time during the training error keeps going down, but whereas the test error start increasing. That's when the model will get overfitted. Also, you can see in this particular chart on the left-hand side, we have the training error and the testing error like goes up as we train more into the epoch, whereas the desired convergence is shown on the right, where both training error and testing error starts going down as we train more into the epochs. Data augmentation has many other advantages in addition to reducing overfitting. It can produce faster training, increased accuracy of your neural network model, and also it can help you to increase your data set size. And it makes your trained neural network model invariant to different aspects of the data set, like translation, size, illumination, location, mask. Some of this I will show into my future slides. Also, the data augmentation can help you to get hard to get or rare variations to the data set. So when you look at the data augmentation history, the data augmentation is not new. In fact, one of the factors which has contributed AlexNet to win the ImageNet challenge in 2012 was the use of data augmentation. They have increased the dataset size to a factor of 2048 by randomly clipping 224 by 224 patches, doing various color augmentations, randomly flipping the image horizontally, and randomly resizing them. And all of this have helped the AlexNet to increase the accuracy by 1%. So it helped to reduce the error rate by 1%, and that helped them to win the challenge. So before I go through the details of data augmentation, I want to go through the common use case of data augmentation in computer vision. As you can see in this diagram, there are 3 use cases. One is called the image classification, object detection, and segmentation. So in image classification, as you can see here, you are classifying an entire image into a category. So in this example, is this a cat or a dog? Whereas in object detection, you classify the objects in the image with the corresponding bounding boxes. So here the object, the cat and the dog is classified with the corresponding boxes around them. And in segmentation, each pixel in an image is classified to a class. So every pixel in the image is associated with a particular class. So these are some broad categorization of data augmentation. So I have categorized them into 5 different categories. The first is color or illumination augmentations. So those are some examples of those are brightness adjustment, contrast adjustment, saturation, blur, hue, color temperature, VNet, etc. And then you can add a bunch of effects into your data set by doing a effects or augmentation. And some of them are like rain, snow, glitch, noise, adding noise to your images, and gamma correction, and make your image look like they are from water. So that's called water augmentation. And then you can also apply a lot of geometric augmentations. And some of them are flipping the image, resizing, cropping, warp affine transform, scaling, rotating, and perspective transforms, etc. And also there are a lot of filtering augmentations like box filter, Sobel filter, Gaussian filter, noise filter, median, etc. The last category here is called mixing augmentation. So this is more like completely like destroying the original image to make it look like some other image and still make the network recognize that. So they are like blend, non-linear blend, crop and patch, erase, random erase, a random image crop and patch. So I will get to the details of this in my future slides. So first I will go through the color and illumination augmentation. So here, if you can see that this is one of my friend's cat picture, which is applied with a bunch of color and illumination augmentation. So you can see that the original image is adjusted by changed by brightness, contrast, saturation, color temperature, and VNet. And all of these images were generated by the AMD's MI Vision X toolkit, which has a ROCM augmentation library. So we use the functions in that to generate these images. And here is the geometric and displacement augmentation example. So the original image is horizontally flipped, cropped, resized, rotated, vertically flipped, and warped. And even we have a fisheye effect. So fisheye effect can be useful in virtual reality kind of applications in computer vision. So the last category, as I mentioned before, is the mixing augmentation, and they're more like a disruptive augmentations. So you can see that the original image is like destroyed kind of by blending it with the cat image is blended with a dog image in this example, and it's color twisted, and some part of that is erased by like applying this color patches, and then you can do a blend with some other image called non-linear blend, and then you can do crop and patch. And glitch is like when you have a glitch in your computer or something, it looks like totally different, and you can apply water augmentation, etc. So now I want to go through the details of why you need to have random parameter adjustments and how they can be applied to different kind of data set. This is an example of MNIST handwritten digit data set. So if you see the case that this is rotated by 180 degree, if you look at the number 6, it's actually 9 here. And so that is not representing the original character anymore. Similarly, like most of these digits are completely transformed and it doesn't represent the original image. So if you are applying a rotation augmentation for this data set, you might not want to rotate more than plus or minus 30 degree or something. You will only want to rotate like a slight amount, so it won't destroy the original character. Similarly, if you see the flip, and also the flip is not a good augmentation for this data set, because when you flip those characters, the digits, they are completely looking different and it doesn't represent the original one, except for a few of them like 0 and 1. So maybe flip is not a good augmentation when it is coming to this particular data set. So here I am showing an example why the random geometric augmentation like rotation or flipping or that is important, right? So so what happens is the random parameter adjustment can help in almost all augmentation types. So this is because in real life, the data can exist in a variety of conditions like low lighting, grassland, rain, snow, etc., and which can lead to inappropriately labeling frozen lake shores as glaciers or even missing some objects entirely. You remember that Uber self-driving accident missing a pedestrian in 2018 happened in Arizona. And this is entirely happened because of low lighting condition, and the system in the car which is doing the inference failed to detect a pedestrian because of the low lighting condition, and that caused a fatal accident. And you don't want that to happen to your neural network model. So how you make this parameter randomized is like you have a random function. So in this particular case, I'm showing a random parameter for the strength, which can vary from a negative range to a positive range. And that is chosen randomly for every iteration in your training. So in the bottom, I'm showing the cat image, which has adjusted with a random brightness parameter. And on the right-hand side, it is adjusted with a random noise. Here is another example where I am showing a hypothetical example where random rotation is important. So imagine that you have a hypothetical data set for classifying the class of a car to be Tesla or Ford. And imagine that in your data set, most of your Tesla cars were facing left and most of your Ford cars were facing right. And your Tesla cars were labeled as 0 and Ford cars were labeled 1. And you train your data set without doing any random augmentation like rotation, flipping, scaling, or something. And then you have your trained neural network model, and you, at the time of testing, you give a Ford car, which is facing left. And you might have guessed it correctly, this trained neural network model, the human being can really identify this is a Ford car, but the trained neural network model, which was trained with this data set, will identify this as to be Tesla car, which is wrong. So this is an extreme example, but I'm showing this to understand the importance of doing random or like geometric augmentation while training a neural network model. So the next part of the talk I am showing is when you train a neural network model, you have your images, but and for a lot of data set, you have the metadata, which can be your label, your bounding box, or your segmentation mask. And when you train your neural network model, in addition to training your like doing the augmentation in your images, you have to also do the augmentation in the metadata. So these are the examples of data augmentation, which is applied to image and metadata for the bounding boxes. So here, this is the original image. And this is the original image with the, this is the original image and the original image with the cat and dog bounding boxes. And when you resize, you see that both image and the bounding boxes get resized as well. And the flip, both image and bounding boxes get flipped and cropped. So you can see that the image gets cropped and also the bounding boxes. And here is the thing, when you rotate, you still need to make sure that the bounding boxes can represent the image just like the objects in that particular image. So these are some examples of metadata augmentation when is applied to the image and the corresponding mask image. So this image, the giraffe image, is taken from COCO data set, and the mask image also comes as a in the annotation file as part of the COCO data sets. So if you see that the first category is the image and the mask, and then when it is flipped, it gets flipped, both image and mask. So when the second one is, the third one is the color twist. So here you can see that the image is color twisted, but you don't need to apply that transform to the mask. Then it will completely look different because the mask is actually representing a category in the original image. So it shouldn't get color twisted. So when you actually crop both image and mask gets cropped. So the interesting fact here is that the geometric augmentations like rotation, flipping, cropping, and resizing, they apply to both image and mask, whereas the illumination augmentation only apply to the image, not to the mask. So this brings down to the next part of this talk, which is how to build a training pipeline with augmentation. So we have learned about different kinds of augmentations, and important of metadata augmentation and how it applies to different data set. Now let us look at how to build a training pipeline with those augmentation. So as you can see that here you have your training data set, which can come from a camera or images and all. And first operation you have to do is to load and decode that image. And that can be done using CPU or GPU. And then you have a augmentation like library or something, which can do a bunch of different augmentations, either using CPU or GPU. And then after you do that, you will get a ready to train data. And that can be given to one of these frameworks like PyTorch, TensorFlow, Caffe for training or inference. So let's dissect a bit more into the operations in a training pipeline. So as you can see that most of the training pipeline will have a data iterator, so which goes through the images and labels. So you will have an enumeration function and you run that enumeration script and then you do the augmentation. So, so when you consider the data set, so it goes through a data set class for reading and decoding. So, sorry. So first it goes through the data set class for reading and decoding, and then it goes through the image augmentation. So in this example, I'm showing a resize followed by a cropping, mirroring, and normalizing. After that, you get the output tensor, which is in the form of, after you do the normalization, the RGB image, which is decoded, will convert to a floating point tensor. Because most after normalization, the range of the data is for 0 to 1. And I don't want to go through the importance of normalization when it comes to the data set. That's another topic, actually. So along with the images, your metadata also go through the metadata reader. So if it is Cocoa data set, for example, you need to read the JSON file for the annotations and get all the metadata, which can be labels, which can be bounding boxes, segmentation mask, or key point. And metadata also go through metadata augmentations. And at the end, you will get your ready to train labels, bounding box, and mask corresponding to this output tensor. So this is actually like a little bit part of the code snippet, the Python script for doing that augmentation transforms. So as you can see that most of the augmentations is done by the torch vision transforms. So if you look at the here, so I have transform functions defined here, which does resizing, random cropping, random horizontal flip. So first the image is decoded. After that, it is resized to 300 by 300 size. And then from the 300 by 300 size, you randomly crop a patch of 224 by 224. Then it is randomly horizontal flipped with the probability of 0.5. That means that 50% of time you flip and 50% of time you don't flip. And then it is normalized with the mean and standard deviation. This 0.5 is the mean for RGB and the standard deviation. So after that, in the PyTorch, you create your data set and the data loader. So in your data set, you're saying that I want the ImageNet for training, and I want the transform to be applied, this transform to be applied to the training data set. And then after you define your data set with the transform, you actually create the data loader, which is the iterator, which I have shown in the previous slide. So you give that train data set with your batch size, and this other parameter shuffling is for shuffling the data set or not. After you create that, and then you call your training script with that data iteration like iterator. Here are some augmentation functions in PyTorch and TensorFlow. So PyTorch and TensorFlow has different augmentation functions, but they pretty much do the same thing. So in PyTorch, they have like the torch vision transforms, which has functions like center crop, normalize, resize, scale, color jitter, etc. So these are more for random augmentations, and they also have functional transform. Functional transforms are more like the random transformation, but it is fixed. So if you want to test out your augmentation without the randomness, or you want to apply the augmentation with a fixed parameter, you can use those functional transforms. And in TensorFlow, they have the so-called lambda functions, which does the augmentation, which is called random brightness, random contrast. And there are functions which doesn't have the random name in it, which is more like fixed parameters. So as I have mentioned, there is a lot of random parameters which play into picture when you do the augmentation for training. But if you want to increase your data set size, you can also use the fixed parameters for getting data which is has a certain change of brightness or contrast adjusted to that. So that brings down to two different use cases for the data augmentation. I call it as offline use case and on the fly use case. So one example of offline use case is like if you have a data set, but it is not good enough and not enough to train a network, and you want to increase the data set size by applying a bunch of augmentation. So in the offline use case, you can get one input image, apply a bunch of augmentation with different strength parameters, and you can produce a batch of images at the output. So this is multiplying your data set. So it will help you get hard to get or rare variations to your data set because you haven't been able to get all the images which represent every conditions in your data set. The right hand side is the on the fly use case. So where a batch of images is given to a pipeline, and then on the fly it does a bunch of augmentation with certain random parameters, and you produce a batch of images at the output. So this is the use case which is used in today's training for whether it is for image classification, object detection, or segmentation. So basically, while training, those random parameters are varied differently. So every iteration you get, a completely different looking set of images. So now I want to actually introduce the single SSD object detection training. So as you may know, SSD stands for single shot multi-box detection. And it was released in 2016 and reached new records in terms of precision and accuracy for object detection, scoring over 74% MAP. So it's both an object detection and classification done in a single pass. So when you train the SSD object detection training, you have to basically train, optimize or train for reducing the confidence, the loss for both object detection and classification, and the network is combined. But there were a lot of challenges in SSD in detecting smaller objects. What happened is, since the maps priors were pre-computed for different feature maps in advance, during training, it was not able to actually capture the smaller object. They disappeared. So how they solve that problem is by introducing a different kind of augmentation called SSD random crop. So in the next slide, I will explain how that is done. So usually, like at the input of your training, you have the image with the bounding box, and the first augmentation you do is called SSD random crop. So basically, the SSD random crop randomly choose a crop of the original image with its bounding box. How it chooses randomly is it actually scales it with a random width and height factor, and also it applies a random aspect ratio, and then you get a crop. But once you get a crop, it is checked with the ground truth bounding boxes to see that if it is a good crop. So basically, in this first example where I am saying that it is a bad crop, what happens is the objects doesn't have a certain IOU. IOU is the intersection over union with the ground truth bounding boxes. So I'm saying that I don't want that crop. So the SSD random crop has a criteria which says that if my crop is greater than, if it has all the crops in the object, if it has more than 50% IOU, then only I want that crop. And that is a parameter. You can choose 50%, 30%, 70%, depending on what you want. So those bad crops were discarded, and then it keeps iterating until you get a good crop. Here, this is an example of good crop because most objects were captured with a good IOU with the ground truth bounding box. After you have that, you will do the rest of the augmentation like color twisting, resizing, and flipping. So this helped to actually reduce like the problem of losing smaller objects when it comes to the training. So now we are reaching the end of this talk. So I want to give some results of data augmentation. So we have, I have done this with the ResNet 50 training, classification training, and I conducted that experiment on a smaller data set of ImageNet using PyTorch. So there are 4 different categories. First, I have done the training without any augmentations in the pipeline. And then I introduced normalization, and then I introduced like random resizing, random crop with normalization. After that, I introduced like the random resizing and random crop mirror normalization. So which is like a fused augmentation, which combining a lot of augmentations in that one operation. So as you can see that in the case where there is no augmentation, my training, the top one training accuracy around like 25 epochs or something reached 91.5%, but my validation accuracy was not that great, it was less. And also the train loss is good, it reduced to 1 something, but the validation loss was not converging. But as soon as I introduce the normalization, as you can see that the train accuracy is still high, but the validation accuracy went up by almost like 6%, which is pretty significant. And the train loss is almost the same, and the validation loss also reduced. So as you can see that after I introduced the random resizing and cropping, the train accuracy increased, and also the validation accuracy, and the train loss became little more, but the important thing is the validation loss went down. With all the augmentations, I get a pretty good top 1 accuracy for training, validation, and the train loss and validation loss also converged. So this is what I want to choose for my training pipeline. And this can be seen from this graph. So here is the left-hand side is the case where with the no augmentation case, as you can see that the training accuracy is going up and it is reaching almost 100%. but validation accuracy is not converging, not going higher, even if you train more and more. Same here with the loss. The validation loss is like staying constant, but train loss goes down. But with the augmentation, as you can see that you can get a nice chart with both training and validation is converging for both the losses and accuracies. So the final part of the talk, I want to actually bring up some of the challenges in data augmentation. So as I mentioned that we have like, I'm here showing the 3 main frameworks for training, which is like PyTorch, Caffe, and TensorFlow. So each framework has its own data loader and augmentation pipeline. So if you look at PyTorch, PyTorch has the torch data class that is called dataset. And then it has a completely different functionalities in Torch Vision, which does all the augmentations. And Caffe has the Proto, LMDB, and all for data loading. And that has its own transformation. It's called image input op. So that is for doing the augmentations. And when it comes to TensorFlow, you have the TF dataset and TF session for creating your data loader iterator. And then they have the so-called map or lambda function for doing the transformation. So as you can see that if you want to do training using PyTorch, and then you want to do the same training on TensorFlow, you have to learn an entirely new thing again and change your code for doing on that. So it's a lot of extra effort from the user to port them individually. So because of that, it is not portable or flexible. So that calls for a unified library, which can work across all frameworks. So your library for data augmentation will be same, but you can just use the PyTorch or Caffe or TensorFlow. So this is the motivation behind the AMD's RawCal, which is the ROCm augmentation library. And with that library, you will be able to integrate it into PyTorch, TensorFlow, and Caffe. And all your optimization are done at a low level, and it shares the same library, low-level library. So you will get all your optimization, whether you train in PyTorch or Caffe or TensorFlow. So please check that out. And data augmentation has many challenges, as I mentioned. So designing an ideal augmentation strategy is kind of heuristics. So whoever using the augmentation has to figure out whether you want to use like geometric augmentation and it's like more a trial and error kind of way currently. So that because of that, it can result in suboptimal training outcomes. And as I mentioned and shown on the MNIST dataset, data augmentation techniques can greatly depend on your dataset. So consider face detection dataset. So when you apply your transformation, the face detection algorithm has to be component invariant, like it should be invariant of hairstyle, makeup, accessory, etc. And also it should be pose invariant. So you cannot just apply a bunch of geometric augmentation. The geometric augmentation becomes important there because it can help overcome some of the pose like invariance. So you might have to invent new augmentation strategies for depending on your data set as well, because the existing ones may not work for all data set. And each of the augmentation use cases has many challenges when it comes to choosing the ideal augmentation strategy. And that calls for a unified augmentation library that can work across all frameworks and can provide both performance and flexibility. To wrap it up, data augmentation can help to prevent overfitting and expand your data augmentation. Expand your data set. Data augmentation pipelines can greatly vary based on the use case. Choosing an ideal augmentation pipeline is tricky and needs some automation. Finally, neural net transfer and GANs can bring an artistic approach to augmentation and can provide some automation. But that is a topic for another talk. So I would like to conclude my talk with a quote. Machine learning is an unfinished canvas, but with the art of data augmentation, we can give it a different perspective on today's computer vision problems. That's all for my talk today, and thanks to AMD for giving me this opportunity, and thanks to my team and my manager who gave me like guidance and support. And these are some references about which I mentioned in the talk, especially the MI Vision X toolkit and the ROCM augmentation library, and the disclaimer. And again, thanks to AMD for allowing me to talk in this conference, and hope everybody like got something from this talk. And I want to see if anyone has questions. Thank you.
Thank you very much. We have a question from chat. And what are your future plans for this technology?
So we are actually like currently supporting like classification and object detection use cases. But in future, we are trying to add more and more use cases. Like we want to support segmentation, we want to support the person key point, we want to support the mask RCN and use case. So we are adding new use cases. Not only that, we have currently like our pipeline can work on CPU or GPU backend, but we want to add the hardware decoding and encoding into the pipeline with the AMD's hardware. So that way the data decoding will be very fast. So those are our future plans for the augmentation library. Did that answer your question?
Yes, thank you.
Mhm.
And that's all questions.
Is there any more question? I didn't hear you. So with that, if we don't have any more questions, I will stop my presentation here. But please feel free to send me email or open questions in the platform. I will be happy to answer them after the talk. And I hope everybody understood something fundamental about doing data augmentation for training versus inference for the machine learning use cases. Thank you. I will stop sharing now.
Do I start immediately or?
You are ready to talk?
Sorry? I don't think I heard you, sorry.
Let's start.
Okay. Just give me a minute. I have to pull up my
You can sharing.
yeah, I'll just start sharing. Give me a second. See my screen.
Yes, in camera.
Okay, so today's talk is going to be on MI Vision X, which is AMD's computer vision and machine learning toolkit for inference. And I would also show you how to use OpenVX within a toolkit like AMD's. So if you have missed out on my colleague's talk previously, you would also be able to get a recap of what OpenVX is and what MI Vision X is. So in today's agenda, we have an overview of what MI Vision X is, what is OpenVX and how OpenVX can be used from a vendor perspective, and also how AMD's MI Vision X can be used across all platforms. And I would also give you an example of how to use MI Vision X for using it as an inference toolkit with a hands-on tutorial and some conclusion following that. So what is MI Vision X? It is basically an open sourced collection of computer vision and machine learning inference libraries, utilities, and applications. It uses OpenVX as an underlying framework and is trying to deliver highly optimized open source code for deployment. MI Vision X can be run on a variety of hardware platforms, including embedded CPUs, APUs, GPUs, and servers. And like Raji mentioned previously, MI Vision X also includes an augmentation library called ROCAL, which is used for training using various frameworks like PyTorch, TensorFlow, Caffe2, etc. So where does MI Vision X fall in the software stack? So on the right-hand side, you can see that you can see AMD's ROCm software platform, which is basically the development platform for high-performance computing. It supports the latest machine learning frameworks and optimized math libraries, and it also provides support for Docker and Kubernetes. So within this framework, on the left-hand side, as you can see, MI Vision X is part of the middleware or libraries part with extensions provided for neural networks, WinML, augmentation like ROCAL, which is the RPP library, etc. We also have applications for MI Vision X, which can be seen in the toolkit level, where users can actually develop applications using the library. And we'll see a few examples of this going forward. So an overview of MI Vision X is, MI Vision X is conformant with OpenVX 1.0.1. What is OpenVX and how it's used would be seen going ahead. We also have neural network extensions and support for a model compiler and a model optimizer. So in this, we take different input models, which are Caffe, Onyx, or NNEF, and pass it through the model compiler parser and deploy it on different hardware platforms. In our case, we have examples of it running on CPU or GPU. We also have the OpenCV interop with it. It also comes with the Radeon augmentation library or the ROCAL. We have ML support, Windows WinML support, and we have some utilities such as AMD Dataset Analysis Toolkit, a few command line tools for testing, and a 360-degree stitching library called the Loom. So in this slide, you can see the various examples that were mentioned in the previous one. Going from the top row left to right, the first one is a skin tone or a hand tracking device detector, which uses OpenVX underneath and all the vision libraries. And it can track your hand movement, and it's an it's a computer vision application. The next one shows how MI Vision X can be used for inference, such as detecting handwritten digits. In this, we use the MNIST Caffe model, and it can recognize digits between 0 and 9. The third one is the RawCal augmentation library, and you can see where a particular image is seen in different augmentations. So you could see a fisheye view, a rotated view, a brightness. These can be multiple augmentations like geometric, color augmentations. It could be logical ANDing, etc., or image augmentation such as brightness, contrast, to just name a few. The next row, we show more applications, and going from, again, left to right. The first one is a Python inference analyzer, which takes a model, which takes a classification model such as Inception, ResNet, or something like that. And it shows you the top 5 classifications for each image that it parses through. And it also shows you what the accuracy for all the top 5 images is in the entire data set. And after running the entire application, it opens the data analysis toolkit, where you can actually see what where the data set can be improved and how it can be improved. The next one shows object detection application, where it takes a live camera input and uses the Cafe YOLO V2 model and detects cars and any automated car application. The last one is what is the data analysis toolkit. Basically, it's used to compare models with different data sets and see how the accuracy changes for different data sets, or train the model multiple times and see how the accuracy can be improved based on the kind of inputs that it is given. Some of the options that you can see on the dataset toolkit is graphs of how many incorrect and correct, or a label summary with all the images which have some labels, and you can classify them according to just one label if you want to, or you could classify them according to one ground truth image and see how it went wrong or where it went wrong for each of these data sets. So how do we use OpenVX within the MI Vision X framework, and what is OpenVX? So OpenVX is an API standard for cross-platform acceleration of computer vision applications. It also provides neural network extensions. To take an analogy of what an API is, for instance, when you're at a restaurant, the waiter comes and takes the order from you and communicates this order to the kitchen and brings you back the food. The API is similar to what the waiter does, in the sense that it takes an instruction from the computer user or an order and returns to the user with a response that the computer gives. So in that way, OpenVX is an open API which can be used by different vendors in their own implementation. OpenVX is unique in the sense that it's the only available Vision API currently, and it is portable between different hardware platforms, and each vendor can build their own implementation by using the underlying framework. It also provides optimized graph functionality, and it can be run on any hardware, and each vendor can use OpenVX to optimize their library or framework to run on their hardware. So we from AMD use MI Vision X and OpenVX to provide an optimized library. So for example, OpenVX takes a camera input and passes it through the nodes, which act as a graph. And there are optimizations which are done on the graph, like memory optimizations for reusable memory or virtual memory. You could fuse a certain number of nodes, and this would give you an optimized graph which can then be deployed on the hardware for user applications. So some of the questions that people have about OpenVX are, is it open sourced? So OpenVX has a sample implementation which is open sourced and can be run on different hardwares, but vendors can also develop APIs, develop their own framework over these existing APIs, and this can either be open sourced or not. Like, for example, MI Vision X is completely open sourced on GitHub, and you can see how it uses OpenVX as an underlying framework. Another question is, are these functions limiting? So yes and no, in the sense that the functionality provided by OpenVX itself are fixed in number, depending on the base features, vision features, or the neural network functions. And vendors can add to these available functions by creating custom nodes for their own usage. This might add some costs in terms of portability, but it's not completely limiting, and users can feel free to add according to their need. The next question is, are the implementations different in functionality? So the core functions that we spoke about, which is the base functions, the vision, neural network, etc., need to be identical across all vendors. So any vendor, the functionality would be different across their platforms. And these implementations need to pass an extensive conformance test suite for using the trademark for OpenVX. And each vendor can submit their implemented version to Kronos, and the Kronos working group would either approve or ask for changes based on how the conformance test passes. These conformance tests, however, are not applicable for the custom nodes that are provided by the vendors. So MI Vision X has one such submission towards OpenVX, and we are conformant currently with 1.0.1 and working on getting conformance with the next version that OpenVX has released, which is 1.3. And once all these functionalities are submitted, like I said, the Kronos group would test this conformance, and you would be awarded the conformant version of your implementation. And most of the silicon vendors, as can be seen, like Intel, Synopsys, NVIDIA, etc., are all conformant with OpenVX vision features. So one of the case studies for OpenVX computer vision, which can be seen on the MI Vision X GitHub page, is what we can see here. It is basically a hand tracking movement for bubble pop, or a hand tracking detector. And you pass an image to the OpenVX framework, and it gives you the edge detection, or the hand tracking detection for a person. How it's done is basically it extracts some of the channels for RGB, and depending on a certain threshold that is set for each of these channels, you can call particular nodes from OpenVX for all of these channel extract, which is like, as you can see, says org.kronos.openvx channel extract. So that's a node which is available in the OpenVX framework, and depending on a threshold, it can do the hand tracking detection. So MI Vision X works across multiple platforms, and here we're trying to show that the same hand tracking movement can be used on a Windows laptop, which is a Windows 10 AMD laptop. The only thing is you would need ROCm supported hardware, which would be an AMD hardware, for using any of the MI Vision X tools or applications. Similarly, we are using an AMD hardware with Ubuntu or a Linux platform, and it can run on Linux as well. And here we see that the same can run on a Mac OS as well. So why is OpenVX useful or better when it's used as a graph? So OpenVX provides graph optimizations, which are like memory optimizations and node fusions, etc., when these can also be used, the individual nodes can also be used as an immediate node and can be used as an immediate node by providing an input. But the advantage of using it through a graph is that it increases performance both in terms of speed and memory by almost 2.5x. So this would be the unoptimized graph or the immediate node execution versus the graph execution itself, which is faster, as you can see, in terms of performance and also in terms of memory, because of the optimizations that OpenVX provides within the graph framework. So how do we use OpenVX inside MI Vision X as part of AMD? So OpenVX is designed to provide basic functionality for neural networks. We add to this particular available functionality by adding an extension for neural networks under MI Vision X. So the flow can be seen here in this the flow can be seen here in the slide. So we take a pre-trained model, which is basically Caffe, Onyx, or NNEF and input, and we run it through a model optimizer or a compiler, which is basically a set of Python scripts. We use this optimized model or NNIR, which has optimizations such as quantization, layer fusion, etc., and run it through the MI Vision X runtime for deployment, for target hardwares. So this shows a detailed photo of the same, which is we take Caffe, PyTorch, or NNEF. PyTorch and Caffe, PyTorch converted to NNEF or Onyx, and we take Onyx, Caffe, or NNEF inputs and run it through the model compiler and optimizer, which is basically what it does is it does memory optimizations, quantization from say FP32 to FP16, and then this is run through some of the applications for deployment. So this is an image of how the data analysis toolkit looks. And as you can see, it gives you a summary of how many correct data is available, how many ground truths are available, and what the top 5 is, and what percentage was mismatched, and for each category of top 1 to 5. We also see in this that it provides different options, like you can segregate them through labels or just go through some of the images that are required. Basically, this toolkit helps to design and develop or retrain or infer your neural network for any of the framework. And this can be run in multiple times. And there is a compare option which compares between different runs and gives you a result, and you can look for anomalies and improve your training or data set based on that. So some of the pre-processing that we add to the MI Vision X is basically augmentation, or things like geometric augmentations, like resize, crop, etc., and image augmentations like brightness, contrast, which is basically the RawCal toolkit. And this is passed through the entire model compiler. And we can also do post-processing on these, such as maybe drawing a box for SSD and models, etc. So this is the entire flow for how it works. So the prerequisites required to run or use MI Vision X is basically a ROCm supported hardware. We also support all OSs, as we saw before. So you could use CentOS, Ubuntu, Windows, etc. You need to be able to build and install MI Vision X on your hardware, or we also provide Dockers, which provides either certain functionalities for just computer vision or the entire flow with all inference, etc. So you could choose what kind of Docker you want to use. So coming to the hands-on part of how to use MI Vision X in an inference format is we have Python scripts which basically take Caffe, Onyx, or NNEF models and convert this to an intermediate AMD NNIR format. And this, it takes the model as an input, the input dimensions, and you need to provide an output folder for it to dump the graph and the binaries itself. So here you could see that on the left-hand side is the graph itself, which is viewed using a tool called Netron, and it shows you what layers and the model contains and what the weights and biases are for each of these layers. And on the right-hand side is the NNIR, AMD's NNIR format, which is basically trying to tell you what the input is and what kind of data it is, which is FP32 or FP16, and what the input dimensions are and the format for the image itself. And it also tells you the output and what the basic initializers are. And locals are basically the virtual buffers which can be reused and optimized. And it also shows what nodes are available, which is basically, as you can see, the first node is convolution, the second node is pooling, and so on and so forth, with the inputs for each of these nodes. So this is the NNIR format of representation. The next step would be to apply the optimizations that we spoke about. So we have a Python script for that called NNIR update. And this takes in inputs such as batch size, fuse kernels, convert from FP16 to 32 or vice versa. And you provide the input as the output of the previous script and a new input models folder, which would be the optimized folder in our case. The next part of this conversion would be to convert the NNIR to the OpenVX C code so that the OpenVX framework understands what the nodes are and how to execute them one after the other in a graph. So you can also specify whether you want to get the argmax and in what format you want to get the argmax for this. So this is an example of how the C code looks. Basically, it tells you that the first layer, if you remember from the graph, was a convolution layer. So it calls the convolution layer node with all the inputs and makes a check whether the node is verified or not. And it does that for each node before actually processing or running the graph itself. The last step would be to apply post-processing on these nodes, like drawing boxes or denoising the image if it is required. And once you have the weights and the converted model itself in the C code, it can be used in various applications for classification, object detection, segmentation, etc. In this, we're showing an example of running an Onyx model, which is an Onyx SqueezeNet model on a live camera feed, and it detects that the image there is a golf ball, and it shows how many seconds it took per frame for, and with what confidence, as in with what accuracy or what confidence the image was detected in the model. Similarly, as we said, we also support Caffe models. So this shows how to use a Caffe YOLO V2 model to detect an object. And on the left side, you can see different color codes for all the classes that YOLO V2 tiny model classes are available, The last one here shows an NNEF model, which is basically a neural network exchange format provided by Kronos for supporting classification models. And here we're using the VGG16 net for as an example. And here you can see that it detects it as a coffee mug. all these steps and the hands-on tutorial itself can be found on my colleague's GitHub, which is open sourced, and you can see all the samples there and use and try it out yourself. The other example that we saw was how we can get all the top 5 and open up the ADAT or the analysis toolkit web page itself, and that can be found on MIVisionX GitHub page, which is a Python inference toolkit, and you can run it by yourself. To conclude, OpenVX is, as I said, a unique in being the only vision API that is available, and vendors can add on to this and provide their optimized graphs and applications. It is also portable and can be used on different hardwares and softwares. The graph-based abstraction also provides optimizations to improve performance for inference and acceleration for a variety of these hardware architectures. And you can go through the MIVisionX website and webpage on GitHub and find all the implementations and applications that I showed you here. I would like to thank Mike, Director of Software Engineering, the entire MIVisionX team, and Timur and Graphicon for providing me a platform to present here today. And some of the resources which you spoke about today is all available here, as you can see. So if anybody has any questions, we can take them now. I'm sorry, I just saw the chat window and it said you guys wanted me to full screen it. I hope you could see the presentation. Otherwise, I can ask Graphicon to see if they can host the presentation somewhere.
Yes, we have a question. What are your adventures over similar products?
Sorry, can you repeat that? I couldn't hear you.
1 second. The question in chat.
Oh, okay. So future plans would be to provide more support for more models. As of now, we currently support.
No. It's last question.
Sorry, you're getting cut off. Are there any questions? So advantages over similar products would be this product itself is most optimized for AMD hardware itself, and can run the best or fastest on just AMD GPU and CPU, and these are optimized for our hardware. So you could use this in our on our hardware, and using our software stack would be able to get the performance on AMD technology hardware itself. We haven't done a comparison against similar products for performance, so wouldn't be able to give you the numbers on those. Any other questions or? I can stop sharing now and hope you learned something and can try and use MI Vision X. And if you have any questions, please feel free to post them on the GitHub webpage, and someone from my team or I can try and answer them for you. And thank you and have a great day.
Thank you. Thank you very much for your talk. In this, the end of now of conference. Thank you.